Let's start by looking at a reflection. So you've heard the word reflection, like when you look at a mirror, you're seeing a reflection of yourself. Mathematical reflection, really the same idea. You create a mirror image of a shape across a certain line. Think of this green line as like if this was a piece of paper and you folded that piece of paper over that line, these two shapes would match up perfectly, A to A, B to B, and C to C. And so it maintains that relationship as you move that line. So imagine I moved the line where I was folding it, that would change where the copy of that shape would land. And so you can move this line all over the place. You can make it so that the line of reflection is actually through one of the points or even through the middle of the shape, and it will keep following the mathematical definition of a reflection. So to get an idea of what's going on here, I'm going to switch over to OneNote so I can draw on there and take some notes. So for reflection, reflection is kind of the mathy word. The non-mathy word for reflection is often referred to as a flip. So you're basically like flipping that shape over this line. And this line has a mathy name. This line is called the line of reflection. Which is a type of line of symmetry. Lines of symmetry just describe relationships between shapes and their copies. When one of these transformations is performed on that shape, and you end up with a design that is said to have symmetry. This design has reflection symmetry. And so to understand where the location of the copied points are ending up, like what determines where those go, we're going to draw some lines. So if I draw a line connecting A to the copy of A, B to the copy of B, and C to the copy of C, you might notice a couple things. First of all, those lines always cross the line of symmetry at a 90-degree angle. That is part of the necessary design for creating reflection symmetry is lines connecting points to their copies have to cross that line of reflection at a 90-degree angle. If they're crossing that line of reflection at different angles, you end up with a new shape that's totally skewed. It's kind of like one of those warped mirrors that distorts your image. The other thing that has to be true is the distance of a point to that line of reflection is equal on both sides. So point A is the same distance from the line of reflection as the copy of point A is, this point from that line of reflection. So those two measurements are the same. We could do the same thing for this line down here. C and the copy of C are the same distance from the line of reflection, and B and the copy of B are the same distance from that line of reflection. And so if those two rules, the angle at which those lines meet the line of reflection and the distances of those points from the line of reflection, if either of those rules are broken, you end up with a warped shape. It's not a perfect reflection. Like when you look in a mirror that's warped, you look at your own reflection and it's all warped. It makes you, it makes you super tall and skinny. It makes you short and stout or something like that and distorts you. Same thing would happen if we didn't follow those rules for a reflection. So next we'll look at a translation. So to go back to the manipulative that you hopefully tinkered around with, here was our translation. So notice this one, there's no flip. There's no, the shape isn't rotated. It's not reflected or flipped or anything. It's in the same orientation, same way that it's arranged on the page. It's just moved up or down over from the original spot to a new spot. So this is often called, a translation is often called a slide in non-mathy terminology. So I'm going to switch back to OneNote again. And we'll take some notes on what's happening when we do a translation. So we're going to do that same thing with a translation. First of all, the non-mathy word for translation is a slide. And we're going to draw lines connecting original points to their copied points. The little apostrophes that you see on these points, those apostrophes indicate that that point is a copy of the original. And then the one up to the left is the original. So if I draw lines connecting original points to the copied points, all those lines are the same length. And also those lines, you could describe it as having an angle also, um, like an angle from a horizontal line. So this shape's been translated down to the right at um, whatever angle this might be right here. And it's been translated by a distance, whatever the length of those lines are. So all the points on the original shape are moved the same distance and in the same direction, often described as an angle, to create a translated copy of that shape. So we would say this design has translation symmetry when we perform that operation. So our third geometric transformation is a rotation. This one is usually the most complicated one because it has sort of the most parts to it and the most characteristics that have to be described to understand what's happening. This one's a little bit harder to see, but I'll show some notes so you can kind of understand what's being done to the original shape to create the rotated shape. So this one, instead of moving along lines, this one has a point that things are rotating around. A little easier to actually see what's happening if you make the point that it's rotating around, that green dot, one of the points on the shape. So you can see now I'm rotating that shape around point C. And you can also see that we can measure the angle that it's being rotated at. So right there's a 90-degree angle. It's been rotated counterclockwise 90 degrees. That's about 180 degrees. 270 degrees, 360 degrees brings it right back around to the start. But that point doesn't have to be one of the points in the shape. It can be out here. And so now the copy of the shape is rotating around a point that's not part of the shape itself. And so on this one, because we don't have lines drawn connecting points to their copies or points to that green dot, it's kind of hard to see the relationship. So as before, I'm going to switch over to OneNote so I can draw some of those lines relating to the original shape and its points, the copies. So with a rotation, just like with the reflection, we had a line of reflection. This one has a point of rotation or center of rotation. So this point right here is often called the center of rotation. That point can be anywhere, just like you saw in the simulation. Oh, I almost forgot the non-mathy term for rotation. We call that a spin. We have flips, slides, and spins. So with this one, we could draw those lines again, but this time we're not going to draw lines to their copies. We're actually going to draw lines connecting points and their copies back to the center of rotation. So if I draw lines connecting C and C's copy back to whatever that center of rotation is, two things you'll notice. First of all, those lines are the same length. Second of all, those lines meet up at whatever the angle of rotation is. Angle of rotation can be anywhere from 0 to 360. You can go clockwise, you can go counterclockwise. So that's how we would describe this rotation. So you can see that this was a 90-degree counterclockwise rotation around point O. If I draw those lines from my other points, from A to A, back to that center of rotation, I have those same characteristics. So those two lines are the same length, and those two lines meet at a 90-degree angle. And if I drew this for point B, it would look like that. Notice they meet at 90 degrees. Those lines are the same length. So you can kind of think about the points of the shape as being attached to the ends of hands of a clock. But with this clock, the center of the hands of the clock being at point O, when those hands move, they all move in the same direction and at the same speed, unlike an actual clock where the seconds, hours, and minutes move at different speeds. Think about these points as being connected to the ends of hands of a clock where the hands are moving at the same speed and in the same direction. So those points have to stay the same distance away from the center of rotation, just like the tips of a hand of a clock. They don't change as they go, and all of those points move together. So that, for all of these, that keeps the characteristics of the shape and its copy the same. So you have congruent shapes in each case. So if you slide, flip, or spin a shape, but you follow these rules and you don't change the angles, the side lengths, the area of the shape, you end up with congruent shapes. Congruent just basically means they are the same, just like identical twins. Those two people are more or less the same in their physical characteristics, but they can be in different places and in different positions, stuff like that at the same time.